Hejsan allesammans, mycket varmt välkomna till dagens populärvetenskapliga föreläsning. Den här lokalen blir alltså en föreläsningslokal nu klockan 12. Och det betyder att om ni vill sitta tillsammans och prata så föreslår vi att ni sitter inne i restaurangen eftersom det här kommer att vara avlyst för föreläsning. Jag heter Zoe Lundqvist, jag är projektledare för universitetets populärvetenskapliga arrangemang. Det är min glädje att tillsammans med våra forskare få sätta samman och presentera våra föreläsningar i det här huset. Det här fantastiska huset är ett samarbetsprojekt mellan Ingenjörsvetenskapsakademin, Luleå tekniska universitet och LKAB. För oss tre partners är det här är Vetenskapens hus en möjlighet både att finnas mitt i centrala stan och samverka med olika lokala aktörer, men också att en möjlighet att få berätta om den forskning vi bedriver och att få bjuda på vårt nätverk av forskare, av intressanta personer som har mycket att säga. Den här våren så gör vi 2 föreläsningsserier. En på onsdagar som är en bredare allmänvetenskaplig föreläsningsserie och en så här på torsdagar som är mer orienterad mot teknik och framförallt ett av våra starka forskningsområden som vi kallar för intelligenta industriella processer. Intelligenta industriella processer. Idag så är det 2 herrar som ni kommer att träffa. Det är Michel Cervantes som är professor i strömningslära och det är Khalid Atta som är forskare i reglerteknik, control engineering. Föreläsningen kommer att vara på engelska. The lecture will be in English and the title is Wide Operating Range of Hydraulic Turbines. It's all about increasing the efficiency in water turbines. And these 2 persons, these 2 gentlemen has promised me that they will begin easy. They will begin light to understand and they will increase the difficult level as they go along. And I, for one, doesn't know anything at all about hydraulic turbines. So I'm looking forward to learning from the 2 of you. Most welcome, Khalid and Michel. I'm looking forward to this lecture, and I know that our audience also is. The stage is yours.
Good day, everyone. My name is Khalid Atta. I'm a researcher at LTU in Control Engineering Group. Before starting talking about the wide operating range of hydraulic turbines presentation, I will present today the AutoFlex project that we have it here, AutoFlex theme, which is that the wide operating range of turbines are belonging to this theme. Before I start, I would like to say that our system autonomy and flexibility, it's a part of the larger theme at LTU, which is intelligent industrial processes. It's just a theme that it's working on connecting different aspects of daily life to improve the technology in industrial processes to provide more robust, more secure, better and efficient industrial processes. By itself, the intelligent industrial processes, or as we call it, IIP, is part of a larger area of excellence at LTU, which is the area of excellence in research and innovations, and which have many parts and sub-themes, as you can see here. Why we need autonomous and flexible system? We need autonomous and flexible system because in the current life, things become much complicated. We have different systems. We have a lot of intelligence distributed over different systems. We have smart cars, we have smartphones, we have a lot of things that have intelligence built in. Our objective here is how we can make all these components operate and work together in a better life. These complex systems, if we consider it interconnected all together, how can we bring a better understanding for the human beings to get maximum benefit of these tools? So what we are doing here, we mainly exploit the complexity of these things. These complex systems are really getting more and more complex, and for that reason we need to able to handle this complexity. The problem here, this type of complexity is very difficult for humankind to understand or to make it integrated all together. So for that reason we have the autonomous and flexible system theme. The autonomous and flexible themes had a focus which is system can learn from each other. We need to put a methodology that the systems can operate and interact between each other and try to discover the way that they can operate in better and efficient way. The vision is that we don't need any human in the loop. That's our vision in AutoFlex project. We need everything to be automated, and it's flexible when something missing, something new added, and new things that may arise. The aim is to foster research on this theme, mainly. Now, I will hand the stage to Professor Cervantes to start presenting the main theme about which is called wide operating range of hydraulic turbines.
Okay, thank you, Khalid. Bon appétit for the people eating. So my name is Michel Cervantes, and I'm working at Lille University of Technology at the division of fluid mechanics. And my research is mainly concerned with Hydric turbines. So what does it mean, wide operating range of Hydric turbines? It's what we would like to have. In fact, it's hydraulic turbines able to operate with a larger variation of flow rate. I will go and present some hydraulic turbines and explain how they are working. But to start, I will show you what is the situation today about the energy and the consequences and which alternative we have. And this implies some consequences also for hydraulic turbines and the need to operate hydraulic turbines with a wider operating range. You will see that hydraulic turbines are already extremely efficient machines. So if we are looking today, we are using a lot of fossil fuel, and oil, coal are not so good for the environment, and they are not so good also for the health of people. Natural gas, when it's burned, it's pretty good, but when you extract natural gas, you may have some leak, and if you have some leak, which is about 3 to 6%, you have some methane, which is also going in the atmosphere. And the methane is like 80% worse than the carbon dioxide. So main consequences of the use of fossil fuel, it's global warming. And that is something that we hear quite a lot in the news. The World Health Organization plans that between 2030 and 2050, it will be about 250,000 people dying every year due to global warming. Another issue which is perhaps less known to people, there is a health problem due to air pollution. And there is in fact several million of people dying every year due to fossil fuel. According to the World Health Organization, it's about 7 million of people dying, mainly in Asia, China and India. So if we are looking today, so the line should be a little more to the right, where in 2017, you see that you have the liquid fuel, natural gas, and the coal, which are widely used today. And renewable energy, it's one of the solutions, instead of using such type of fossil fuel. So renewable energy is going to increase quite a lot. Today, the main source of renewable energy is hydropower. It stands for about 71% of the renewable energy. So which type of renewable energy are we going to use in the future? What is coming? So it's mainly wind and solar energy which is coming. So solar energy, the price is decreasing very rapidly, and it's the same also for wind. And today in 60 countries around the world, solar energy is the cheapest energy that you can get, in fact. It's cheaper than fossil fuel. So in Sweden, solar energy, it's perhaps not widely used, but wind energy, it's increasing and getting some momentum, and at some times we get 10% of the electricity production, which is produced with wind energy. Solar and wind have some exponential growth. And here you can see from several years back, from 2000 to 2013, for the solar, how is it increasing, like the accumulated power, and also for wind. And this trend is going to increase, to increase, to increase. So one of the main problems with solar and wind is intermittent energy. It means that if you start to get some cloud, your solar panel are not going to produce electricity. If the wind stops to blow, you are not going to produce electricity. So it means that in your system, you need to have some backup, which will be able to respond to such type of variation due to the weather. So in Europe, one way to see the quality of the electricity, so we have production and we have the demand, we should have a frequency of about 50 Hertz. And this frequency should be in a certain range. So here you can see some perturbation which happen on the Swedish grid. And we got a frequency decrease really quick. And after, it means that you need to start some machine. You need to regulate here. So in Sweden, we are really lucky because we have a lot of hydropower. You certainly know that about 40 to 50% of the electricity production is hydropower. And we think that in the future, hydropower is going to have an increasing role. It's going to be more and more used for regulation. So the use of hydropower to compensate grid fluctuation due to the introduction of renewable energy, such type of solar and wind, is an opportunity because there is today a large amount of hydropower which is built in the world. As I say, it's the largest renewable energy in the world with about 70%. If we are looking in Sweden, it's about 40 to 50% of the electricity production. And we're here in Luleå, and you have the Luleå River, which stands for about 10% of the total electricity production in Sweden. So some words about hydropower and how is it working. Usually, you have a dam, and the dam will allow to stock some water, so to build a reservoir, and that you can see it as a battery. So when you need some energy, you will use some water, which will go through the penstock, and after it will arrive to the turbine. The turbine is coupled to a generator with a shaft, and it's going to put in motion the generator itself. So that is going to produce some electricity. And after, the water is going to leave the turbine. Hydropower has been built since many years back and developed. And today, hydropower is one of the most efficient way to produce electricity. The efficiency of large hydraulic turbines is about 97%. And you have a really large machine able to produce up to 700 megawatts of power. So such type of machine has a really large efficiency, but they are mainly built to operate at steady state operation. It means that they are working with a given flow rate and give a really good efficiency. As soon as we start to move from this flow rate, the efficiency is going to decrease and certain flow phenomena are going to appear. I get something here. And if we are looking at the introduction of renewable energy, like solar and wind, this is going to create perturbation on the grid, and it means that you are going to use your Hydric turbines more often at part load or high load, and you are going to start and stop them more often. So it means that you are going to use such type of machine away from the best efficiency, for which they are not really built for. So here you have a drawing of an Hydric turbine. If you remember one of the previous slides, you have the dam, and here you have the penstock. Unfortunately, the pointer is not really working. So the pipe to the left is the penstock where the water is coming, and the water after is going to be distributed to the runner. And the runner, it's the element which is attached to the shaft here. So the flow coming to the runner is going to have a certain rotation, and after it's going to leave the runner. So when you are running the turbine at the best efficiency, the design point, the flow is going to leave the runner with a nice straight direction. When you are starting to move away from the best efficiency, you are going to have some rotation which is left at the outlet of your runner. And this rotation in the fluid is going to create some specific flow phenomena which are going to create pressure pulsation and are not so beneficial for the machine. So if we are using hydropower to regulate the grid, we increase the number of start and stop. And we are also increasing the operation away from the best efficiency. So it's part load and high load. So if we are looking a little more in details in what's happening in the machine when we start it, we'll see that we have a large vortex which is developing just below the runner. It's like a snake. And this creates large fluctuation in the flow and vibration of the machine. And it's extremely detrimental to the life of the machine itself. If we are looking at the regular operation of the turbine, here you can see that you have a red line, which is the optimal discharge. So the machine has been designed to get the maximum efficiency at this flow rate discharge. And you see to the left that you have the pressure pulsation. So if you look at the best efficiency point, you have really low pressure pulsation. And in fact, the machine has been designed in such a way that you can run them during 100 of years if you are running this machine at this flow rate. It's extremely good. When we start to go away from the best efficiency, you see that the pressure pulsation are increasing a lot. There is some flow phenomena which appear, which is known as vortex breakdown. And you see that when you increase the flow rate, also you have some pressure pulsation which is going to start to increase. So all these pressure pulsation are due to the residual swirl, the rotation, which is left in the liquid, leaving the runner. So now I'm going to show you some very nice pictures of what's happening. So to the left picture, we see what's called a rotating vortex rope. So in this case, the pressure is lowered, so we can visualize this vortex rope like a snake. So it's a low pressure, and you get some cavitation there. So just to the top, you have the runner. And this vortex rope is rotating, creating some circumferential pressure pulsation, but also some axial pressure pulsation. So it's creating a lot of vibration. And such type of vortex rope makes that some turbines, they cannot operate below perhaps 70% of the best flow rate. And when you are coming to higher flow rate, you get another type of vortex breakdown, which may create some surge. So you will have all the water in the complete water channel which are starting to oscillate. So this problem, it's not really new. It's known since decades. It's dated from even from 1940s. There is some papers talking about the Raynaud frequency. And a lot of measures have been tested, putting some fines inside the draft tube, different alternatives. And the one which is widely used, it's air injection. So here you can see a drawing of air injection. It's a machine in Romania. So they have some tube and they are injecting some air inside the draft tube. And the main idea is to decrease the pressure pulsation, the amplitude of the pressure pulsation in such type of machine. There is some other way to inject some water. It can be through the shaft itself also. So you don't have to have some element inside the draft tube. Unfortunately, air injection, it's not always successful. So here you can see some amplitude function of the frequency of this rotating vortex rope. And what you need to focus on, it's on the amplitude. So to the figure on the left, you see that you have an amplitude about 0.5. So it's due to the pressure pulsation of this vortex rope. And you want to decrease this amplitude. So you inject some air, and in fact, you can see that the peak is increasing to 0.9. What I want to point out is like air injection, it's not always a successful method, in fact, to decrease the pressure pulsation of rotating vortex rope in a draft tube. So it's a phenomenon which appears, the vortex breakdown, and it's something which has been studied quite a lot by people working in fluid mechanics. And if you look in the literature, you may find some different type of vortex breakdown. So you have the bubble form, you have the spiral tail form, and you have the spiral filament form. So the bubble form, it's something that it's better for us. We get less pressure pulsation. So it's something that we want to move to. And there is different theories about the vortex breakdown, but there is no consensus. Some say that it's a wave phenomenon. Some say that it's a 3D separation. Some other people are towards the instability. And some people are mixing these different theories. And there is one researcher which investigated this vortex breakdown and created some perturbation to move from one type of vortex to another type of vortex. And he was able to move from the spiral filament vortex to the bubble vortex breakdown. And it's exactly what we'd like to do, in fact, in Hydric turbines. We'd like to be rid of this spiral vortex, this rotating vortex rope. And he done some experiment by creating such type of circumferential perturbation. So the project, which is partially financed through this area of excellence, aimed to investigate this alternative for Hydric turbines. So what we're going to do is we're going to create a circumferential perturbation to move from a spiral vortex breakdown to a bubble vortex breakdown. And here you can see these two pictures where we have this bubble vortex breakdown and this spiral vortex breakdown. So if we look a little more in details, here to the figure of the left, you can see a runner. And here's this runner, it's numerical simulation which have been performed. So you see the green snake, which is this rotating vortex rope. And after at some plane, we're going to create some perturbation with some linear motors. And here you can see a picture to the right, how these perturbations are going to be introduced into the system. So we may create perturbation with different amplitude, different frequency, with some phase shift, and so on. So if we are looking at the planning on what we expect to do, so we are going to start with a small turbine at the university with a small diameters, just to investigate the phenomena and the applicability to Hydric turbines. And there is a large number of parameters to investigate, such type of the frequency, the amplitude, the form of the perturbation, the phase shift between these different cylinders, and so on. And of course, we want to move from this spiral vortex breakdown to bubble vortex breakdown with a minimum amount of energy. So there is some optimization which are needed. And here, in this case, it's Khalid which is coming.
Hello again. So we conclude here, we have a problem that if we try to control it, sometimes we make it worse, right? By air injection. It's a good solution, but it's sometimes you can make it worse, actually. So we need to know how to do that. And usually this will lead us to optimization. This is our area, actually. What's its optimization? Optimization, it's something that built in our actually DNA as a human. If I will go to my office, I will talk the shortest distance. So I optimize to minimize the time. If I will try to eat, I will eat the best food that make me feel better sometimes. Or sometimes the best food that make me get less weight. Sometimes when I want to take the road, I will take either going, okay, I will choose, for example, the minimum fuel, or sometimes I take the minimum time. Sometimes I take less traffic. So it's an act that it's built in our human action, actually. All our actions in human, sometimes it's built around some objective that I want to achieve. Minimize energy, maximize comfort, minimize expenses. All these things that are built actually in our DNA. Optimization is well now established in the world. For example, as we say, we have 97% of efficiency now in our turbine. What's meaning efficiency? The hydropower that it's entering the turbine, I will extract 97% of it in the output. But you can see previously the water wheel have 10% efficiency. So it's increasing actually over time. These things are design optimization. When I design the turbine, so it's a pre-operation, I call it. But in real life, we need to do optimization online. For example, I drive with GPS, and GPS continuously calculating the optimal path. This is, for example, is an optimization. We, as a process control or automatic control, we have two types of optimization problem. For example, I know my comfort zone at this temperature. When I enter my room, I know for sure the temperature that's best my feeling is 21. I will set it to 21. So for that reason, as you saw here, I have a plant and I know the reference. I know how much the output that make me comfort. So I know the optimal operational point that can operate the plant. And sometimes, for example, here in the house, as I said, you set the temperature you need. You set the cold in your refrigerator. You have the set point that will achieve the optimality you're looking for. But in some other plants, you have no idea about what's the position. Let's take 40 years step back when we have this old radios. What we were doing, I was just continuously holding the knob of the radio and start to change it until I hear the clearest signal. There is no bands like today. I set it on FM 90, 89.1, and I will get that channel. Previously, it was manually. So at these days, consider our problem. We don't know the optimal, where is it? I just seek to reach that problem. And this is what we have here. We need a controller that will maximize, for example, the plant output till I hear the clearest signal in my ear. Like I will point my solar panel till it reach exactly the sun and try to track the sun, because there is no fixed position for the sun. If I don't have the right trajectory of the sun, I will start to seek it. And the controller will do that, actually. This is our objective. We have a subject that we are in control engineering. It's called extremum seeking control. Extremum seeking control, actually, it's a three word. It's extremum, which is the greatest or minima, it's extrema, it's either maxima or minima or a subject. And seeking, we try to achieve. We don't know what is it. We don't know the value of the maximum. We don't know how much I should steer my signal to reach the optimal, but that is it. And control, it's actually, we achieve, we try to control the signal till it seek and reach this optimal. So consider it like this way. Now I'm talking about maximization. Consider a plant which have this nice shape. This is the relation between input and output, right? For example, in the radio, the position of the knob, if you start to increase the position of the knob, you start to hear better, 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 and then after a while you start to degrade. So there is an optimal point. You don't know what is it, and you don't know the position of the knob that will achieve this optimal. What the controller here, the extremum seeking controller here actually do, it's actually trying to achieve both the maximum output without going to it. How that can be achieved? Everyone from mathematics, we know there is the slope. It's actually, in the knob, you start to perturb a little bit. And you see, if I go left or right is better, you just start to do that. Okay, if I do to the left, I will get more. So what you insert perturbation. And then you measure how it's better. And you start to increase and following the slope. So if you are below, it's better to go up. If you are switching and you feel the left is better, you start to increase and going to the left. So it's all about gradient. Everything around the gradient until you reach a point, whether you decrease or decrease, increase or decrease, go left or go right, will give you almost similar thing. This is how it's happened. For example, you can see it in this surfing issue. The try to go left and right until reach a point he gets, for example, maximum speed, or get balanced, or not fall actually. Or this driver on single wheel bicycle, how he tried to go forward and backward until he reached the point that will achieve. How we do that? Actually, we start to insert a perturbation signal. This is what we do by the knob of the radio. We start to put left, right, until to do that. Then I will use a multiplier, high-pass filter, just filtering the result I get and compare it to the input. And I can see here a simple example actually on how that it's going. Assume I have a plant that's having phenomena at zero, maximum at zero. And this is the input, actually. I start to insert a sinusoidal perturbation in the input. Then I start to measure the gradient, and I start to steer my system. Because the gradient is positive, I will start to increase theta until I reach the maximum. And you can see when the output reach the optimal, sorry, it's stopped. When it reaches as the optimal, the system gradient actually reach zero. And that's meaning you reach the optimal. This is simply what you want to do to maximize or minimize things. The question now, this is theory. And most of the time we say, is it applicable or not? We give one example here in real problem. Maximum power point tracking in hydro turbine. When I have water coming through, I want to extract maximum power of it, right? So what we do, we try to adjust the turbine speed in small, micro, or micro or nano hydro turbine, which is a small that you put it in river or in your house, owned by people that having river going through their places or some water source. We will try to have maximum power of this unit because the water will pass whether we like it or not. So all what I need to do, I need to increase the power extracted from that. And we can see here the example simply in that. This figure may be a little bit not clear, but the top side here actually is the turbine speed. This is the turbine speed. The more dark red area, that's meaning you get more power. So we can see when the system started in non-efficient point, the controller immediately move to the red area. That's meaning the system going to have maximum power. And that's clear here by the lower figure. You increase the power. The percentage of the power is very low, and the measurement is noisy. And that's good, because this is a realistic problem. We don't have this smooth sinusoidal or smooth measurement, and we have it in simulation. So this is a real experiment, and the system can reach the optimal. And when we start above, we start in very away from optimality, the system immediately drives the system to the same red area, and it's clear here the power is converged. This is another case when we have sort of instability in the turbine. The turbine is not good actually, but the system, although could extract, could drive the system to the optimal maximum power, even when you have very, very bad measurement. So in that slide, we prove this application is applicable. We can do that actually. But what we want to do now, we want to move to the real problem here. This is what Michel was saying previously. Sometimes you try to improve, but you don't know how. And that's the times that the air injection failed actually, because they try to inject in the improper way. Instead of decreasing the pulsation, they put a wrong phase, wrong magnitude, wrong frequency, and that caused more deterioration to the system. They increase actually the problem. And for that reason, we will have this technique that will be more or less a gradient estimator, and we will use the Extremum seeking controller. But in that case that I showed earlier, we will try to maximize power. In this case, we will try to reduce the pulsation. So our measurement here actually will be simply the Y here. It's the vortex indicator. It's just an indicator, like it's the pressure sensors or pulsation sensors, or even if we go for small scale, we can use visual inspector or a lot of techniques. It's just an indicator of how much wrong operating point we have. And what we will try to adjust here is the frequency and the amplitude and the phase shift of the system. And by that, we will be able to actually get rid of this red snake, as Michel called. In general, we started at LTU in the lab to do this. We have a small test rig there, and we started to develop our own control system that control these things, and we hope we will have a concrete results soon that will show how this can be done in similar manner to the hydro maximization power. So it's the same problem. Instead of increasing your power, we just need to simply minimize your energy, minimize your disturbance. It's back now to Michel.
It's back to me, okay. Yes, just to thank the people who are financing this project. So it's the area of excellence intelligent industrial process, and we have also the Swedish Hydropower Center. So the Swedish Hydropower Center, it's you have all the industry working with hydropower, which are in this center, and it's partially financed also by Energimyndigheten. And in this center, you have Luleå University of Technology, you have KTH, you have Uppsala, and you have Chalmers also, which are involved. And it's, in fact, quite a unique center in the world, because you have research related to turbine generators, but also dams, river. So it's quite unique, and you have a large amount of researchers working. So thank you to them, and please, do you have any questions?
Thanks a lot. As Michael and Khalid says, it's open for questions. If you would like to either question something or discuss something or ponder over something, please raise your hand so I will come out with the microphone so everyone can hear your question or your thoughts. Anyone? For how long do you think this project is going on? You said soon. What is soon?
So this project is going to be on at least 6 years.
6 years.
6 years.
Oh, this year. Okay.
So at the moment there is Khalid and there is myself working on it, and there is also a master student.
Yes.
So at the moment it's about investigating the question,
yeah,
to see if the concept is working or not. Is it something which is applicable or it's not applicable to Hydric turbine? So we're going to start on a small test rig in the laboratory. If it's successful, we will certainly move to the laboratory in Elfkarlebu, Vattenfall laboratory, where in this case we will apply this technique on a model test rig. So now we're talking about a runner which is about 10 centimeters, and we will move to something which is between 30 centimeters to 50 centimeters. So it's pretty much a good turbine, developing about 100 kilowatt. And the idea will be to test the concept on such type of turbine, because such type of turbine model are in fact geometrically similar, exactly the same as the big turbines that you have in reality. So if it's working after there, we hope to move to the prototype, so the larger machine. And at Luleå University of Technology, we have the great opportunity to use the Porteus Center, where we have 2 full-scale machines available for research and development. It's 2 10-megawatt machines. And we can use them for education and for research, and it's quite world-unique opportunities. So it's... I hope this project is going to be on until everything is working and it's applied on the prototype. But we need to go step by step to see that the concept is effectively working, and after to see if we can scale it to larger and larger turbines and so on.
Yeah. Thank you.
So after it's a matter of financing also the project.
Yeah, that's always the question.
But it's a main issue, in fact, in Hydric turbines now, because they are going to be used more and more for regulating the grid. So we will use them more and more during transient operation. So we'll change load. We're not working at the best efficiency. We'll use them so they will be more start and stop. And in fact, it's already something which is happening since the 90s with the deregulation of the electricity market. And also since some years more and more due to the stronger introduction of wind power. I'm talking about Sweden here. So it's something which is already actual, but we believe that it's going to increase also with time. So.
Okay, thank you. Anyone else? No. Perhaps you would feel more comfortable to come forward after we have closed and ask your questions then. I will do this now. I will thank Michel and Khalid, and I will give you a brief comment on what is happening during the coming week at this wonderful house. Every day when I go to work, I feel actually quite happy, because I know that I will learn something new, and that is a privilege to have a work where I'm always learning something new, and where my questions always are born again somehow. Thank you for being a part of this learning process, and in that sense also being a part of what the university is all about. Thank you for taking your time, and thank you for making the effort to come here today.
Thank you very much for inviting me. Thank you.
And to Khalid.
Thank you.
The same to you.